So continuing from the last class, today what I'm going to discuss are the further advancements in solid modeling technique, and today we are moving on to the techniques which are most predominantly used in any solid modeling software. So wireframe modeling is one of the most common methods of doing the modeling process. It is one of the oldest methods to represent a solid. Now in wireframe modeling, basically what happens is, suppose this is a tetrahedron that you see. This is a tetrahedron that you see. Now, if you look at tetrahedron, there are four vertices. This is one vertex, second vertex, third vertex, and the fourth vertex. And there are six edges. There are six edges. The brackets actually signify the edges. Okay? Now, in wireframe modeling, basically what happens is, all the information is actually stored in terms of vertex. All the information is stored in terms of vertex, and each vertex has a unique identity. Each vertex will have a unique identity. So in a wireframe model, when you create a solid out of wireframe modeling, there are only two types of information that are stored. First is the topological information, that is the connectivity. So this is the connectivity table basically that you have got. And the other one is the geometrical information, that is the vertex. So what is the vertex? We all know vertex is a point located in a three-dimensional Euclidean space. So the vertex position is again, this vertex is again going to be a unique vertex. It is going to be a unique vertex. So every vertex is going to be a unique. And when you join two unique vertices, you are going to get a unique edge also. You will also get a unique edge. Hence, what happens is, for any type of surface, whether it is a straight edge or it is a curved edge or it is a surface which is developing out of a Ferguson curve or a B-spline curve or a Bezier curve, all the points basically are going to be denoted in terms of the vertex. So that is the simplicity of this process. But as simple as it is, there is a very big problem with wireframe modeling is the non-uniqueness and ambiguity of visualization. The non-uniqueness and ambiguity of visualization. Now, if you look at this object, it has got a circular cross section. There are two curves which are connected to each other. So here what you observe is a two curves, and there are two curves connecting over here. Now, since it does not contain anything regarding the facet information, it is not giving you any facet information. So what happens is, the visualization of the product actually goes according to the viewer. The visualization goes according to the viewer. So for the same product, this is one visualization and this is the second visualization, where this seems to be a pathway, or this seems to be a handle of a basket. So how are you visualizing this product actually becomes very ambiguous and user dependent. And that is why until and unless you render the model, it is very difficult to recreate the exact visuality. And that is the reason why wireframe modeling is not so popular. It is simple in nature, but due to the ambiguous nature of visualization and non-availability of facet information, therefore it is very limited in use, definitely not used in rendering a model or animated sequence of the model, but it can give you a basic idea how the model will actually look like. A better form of wireframe modeling is the BREP model. A better frame is a BREP model. BREP basically stands for the boundary representation system. BREP stands for boundary representation system. Now in boundary representation, basically what is happening is, all the models are actually taken from the base up as we took in the wireframe. Wireframe, again, we are taking the vertices. These are the four vertices. These are the edges. The bracket one are the edges. But over here, you have got an additional information of facet. You have got an additional information regarding the facets. And there is another facet at the back end, that is D. So here, basically what happens is, we have different structure which we called as a winged edge data structure. We called it as a winged edge data structure. And in winged edge data structure, not only we are looking into the connectivity, we are also looking into the orientation. We are also looking into the orientation that I discussed yesterday's last class according to Mobius rule. According to Mobius rule. So this structure becomes better for visualization and better for understanding. So what I want you to do right now is I want you to prepare this tetrahedron in your copies so that we can discuss it later subsequently. So you have 2 minutes. So please prepare this tetrahedron in your copies. So I hope you people have done it. So the winged edge data structure basically consists of an edge table, where edge table consists the edge name, the vertices, that is the starting of the edge and the ending of the edge, the faces on the left side of the edge and the right side of the edge, and then it also has the orientation part over here where the clockwise traverse on the left face and right face gives you the sequence of edges. So as compared to the wireframe only had two information. The first information was the vertex information and the second information was the connectivity information, that is the edge information. Here the edge information and vertex information is there, but the additional information of faces also has been added, which gives you a facet information. So let us start working over here. So suppose we are taking these three vertices and we are trying to create a connectivity out of them. So what happens is, let us start with edge number 3. This is the edge number 3. Okay, so this is the edge number 3. So edge number 3 is connecting between vertex 2 and vertex 4. So edge 3 is being connected by vertex 2 and vertex 4. Okay, now let us assume we are walking on this edge. Along this direction. That is from 2 to 4. Okay, so the starting point of the edge is 2 and ending point is 4. Okay, this becomes your left and this becomes your right. So what is on your left side? Which face is on your left side? Which face is? Yes, A is on your left side, so very correct. Now, sorry. So which face is on the right side?
B.
B, exactly. So B is on the right side. Okay. Now we will discuss of the left face. We are only talking about the left face. What is this left face? This is the left face. Okay. So this orientation is here. What will be the next orientation? This one. And what will be the orientation of this? Because face A is going to be created by which edges? 3, 5 and 1. So 3 is connected between 2 and 4. What is 5? 4 and 1. And what is 1? So since this is the first edge and this is the last edge, so loop is completed. So this is the orientability. Understood, everybody?
Can you repeat once more?
This was the orientation that we had taken. Okay. Now we are only talking about face A. How is face A being created? By edge 3, edge 5 and edge 1. Okay. 3, 5 and 1 will create this face A. For edge 3, you know the orientation. So create the orientation for other edges. So now how the loop goes, this for the loop to close, if this is the first vertex of the first edge, then it has to be the last vertex of the last edge. So see, 2 to 4, 4 to 1, and 1 to 2. So the first vertex of first edge is equal to the last vertex of the last edge. Hence the loop is complete. Understood?
Yes, sir.
अच्छा, अब जाते हैं phase B पे. Let us go to phase B. Now see the phase B. Phase B is going to be created by edge 3, edge 6, and edge 2. ठीक है? So what is edge 3? 2 to 4. What is edge 6? 4 to 3. And what is this? 3 to 2. So again, the loop is complete. So now you come over here. Now see, in clockwise traverse on the left face. Okay? If you look at the left face, this is your left face. Okay? A. Which is the preceding edge and which is the succeeding edge. Okay? That you have to find. So what is the preceding edge on this face? On face A, for edge 3, what is the preceding edge? Preceding माने पहले का. समझ में नहीं आ रहा है?
हेलो
हाँ,
सर फर्स्ट होगा ना?
ध्यान से देखिए, आप इस डायरेक्शन में जा रहे हैं. ठीक है?
यस
लूप कंप्लीट हो गया. ये टेल है, ये हेड है. प्रीसीडिंग कहां होगा? जो टेल से मिलेगा.
यस सर.
हाँ ठीक है, ये फर्स्ट होगा, ये 1 होगा, ये 5 होगा. करेक्ट. ये 1 होगा, ये 5 होगा. ठीक है, ये 1 होगा, 5 होगा. अब एज बी पे जाइए, फेस बी पे. प्रीसीडिंग क्या होगा? 2. और सक्सीडिंग क्या होगा? 6. 2 and 6. ठीक है? तो बेसिकली नाउ if you compare this whole information with the wireframe model, what is the additional information you are getting?
Orientation.
And you are also getting the information regarding the facets which are actually creating the surface. You are also getting the facets which are actually creating the surface. As a result, what is happening is your surface information is getting more robust. As a result, when you render an object and when you visualize an object, the visualization becomes better. So this is the advantage of a BREP model. Now, then there is another operator which we call as the Euler-Poincare operator. Now, Euler-Poincare operator is something which is more like constructing everything with your own hand. Like you are making everything with your own hand. So whatever action you are doing, okay, that action is represented. Now, how it is represented? The first thing is the syntax. Okay, the Euler operator is written in this format. M is for make and K is for kill. Okay, so whatever you are creating, that is the make part, and whatever you are removing, that is the kill part. Okay. Now XYZ basically may represent a vertex, an edge, a face, a loop, a shell, or a genus. Okay, it can represent anything. How we actually do with this Euler Poincare is something very simple. Suppose I want to create this. The only criteria over here is the condition of Euler Poincare. You remember the condition of Euler Poincare? V minus E plus F minus L minus F minus 2 times S minus G equal to 0. This condition has to be always satisfied. Whatever action you may do, you may kill something, you may make something, okay? You may either make something or you may kill something. But at the end of the day, the Euler Poincare formula where value should remain constant. That is how you people will work with this. So if I want to create a vertex, okay? Suppose if I want to create a vertex, what will a vertex actually do? It will help in creating an edge. So when I make a vertex, MEV, I am also making an edge along with a vertex. So I am adding something. Okay? So even if I add 1 and 1 is subtracted, the value remains 0. Okay? Similarly, if I go into the second command, make a face and an edge. So if I make an edge and a face, a loop is automatically going to be created. This is an edge, this is a face, and on a face, orientation is automatically going to be there. So loop is automatically going to be there. Now, if I substitute it over here, you can very clearly see it remains 0. It remains 0. So E is minus 1, plus 1, minus 1, minus 1. It remains 0. Hai na? So whatever you are doing, you can do anything, you can make any operator, but the only thing that you need to do is the Euler Poincare formula has to be always satisfied. Similarly, it goes with the killing part. Please always remember that when you are making a shell and when you are making a face, okay, the loop is always going to be inserted and the loop is always going to be deleted. Please remember that. Okay? Now, let us take a very simple example of constructing a cube with the help of Euler operators. Okay? So the first command we are making is make a shell, a face, and a vertex. So what we have done is we have defined this vertex. And we have defined a shell. What is basically happening over here is when you define a vertex basically gives you a point in a 3-dimensional plane. On that point, across the plane is right now infinite length. The plane is right now of an infinite length. So in order to create a finite system into that, you need to create boundaries. The moment you start to create boundaries, the surface is going to be cut and a model is going to be created. So this is the first step for any sort of geometrical entity that you make. This will be your first step. So make a shell, a face, define a face with a vertex. So a vertex has been defined. With the help of that vertex, a plane has been defined. Okay? And there is a shell on top of that plane. After that, what we have done is make an edge and a vertex. So the first point was already there. We defined the second point and edge 1 has been now defined. Similarly, again we have defined an edge and a vertex. So this is already there. just give me a second, please. This is already there. This is already there. So a third point has been defined and the second edge has been defined. Similarly, when you go to this step, again, we repeat the same step. So now the fourth vertex has also been defined and the edges have already been defined over here. So when you define the fourth vertex and the first vertex, the edge automatically is going to be created. The edge automatically is going to be created. It is going to complete itself because this is going to be the orientation. So due to the orientation loop being generated, it will automatically close the loop from 4 to 1. So edge 4 will automatically be generated. Then again we create another point, another vertex and create another edge. Okay. Similarly, we keep on creating. So now this has been created. Now here what we have defined is make a face and an edge. Make a face and edge. Why? Because the moment it closes, okay, this has closed over here. The moment it closes, a complete face has been created. That is why a vertex has been defined, a edge has been defined, a loop has been defined, and a face has been defined. Okay, so the moment this vertex was created, again the same orientation happens. The same thing happens with orientation. So the loop completes, and then when the loop completes, a face is generated and a loop is defined. Now, once we have identified these points, we need to create another edge. So we defined another edge and another vertex. Once the edges have been defined, we create a face. So the bottom face was created, the front face has been created, the top, the side. Now similarly, we will keep on creating the faces, and at the end, we will simply create the front pass. And the last and the most common process that is available right now, and that is what you people generally do in your day-to-day working with solid modeling softwares, is what we call as a constructive solid geometry, or CSG. This is one of the most simplest methods that is employed right now. It uses primitives, but the primitives are solid models in their own sense, that they can be created from a two-dimensional image. They can be created from a two-dimensional image. There are 6 basic primitives. They are block, cone, cylinder, sphere, triangular prism, torus, and there are many other primitives also which can be user defined. We follow Boolean operations over here, and generally the Boolean operation is union, intersection, and difference. The other Boolean operations automatically come into picture while we are doing the operations. This method is actually a combination of 3 processes: the primitive instancing process, the wireframe modeling, and the BREP modeling. It is a combination of these 3 processes. So how does this system actually work? This system works on a principle of creating a CSG tree. Now, what is a CSG tree? The CSG tree is basically creating a sequence of commands in order to get the desired CAD model as per our description. To get the desired CAD model as per our description. Now, in order to get the desired CAD model, you need primitives. Definitely. You need Boolean operations. Definitely. And you also need the transformations. Now, there are different types of transformations. Some of them you might be knowing, that is shearing, scaling, moving the object from one place to another, that is called translation. Then rotation is there. Then you have some other transformations like resizing the object. Mirroring is also one of the most common examples of transformations. So all these commands are also used in order to create the CSG tree. So I'll just give you a basic example how this CSG tree actually works. So suppose I want to create a block. I want to create this complete block, an L-shaped block. So the first thing what I will do is I will go back and select a block. Okay? So what I will do is I'll select a block. I have selected one block. Okay? And to create this block, what I will do is I will create an object. Okay? Like I'm making block 2 first. So the block 2 is actually something like this. The block 2 is actually something like this. This is what actually the block 2 looks like. And what I will do is after I draw this, this will have some length and this will have some width. I'm not going into dimensions right now. So I have length and width. And the next command I will do is extrude. And then I will give the height. So this is the block 2 has been created. So block 2 has been created. Now, once I give the height, that is what the scaling portion basically means. That is what scaling basically means. Scaling means you are giving a specific dimension to the product. Similarly, what you will do is you will create a small block like this. And again, this will have some length and this will have some width. And again, what you will do is you will extrude it with some height, h. So now, again, the scaling process is done. Now you have what you have got is this is one block and this is your second block. Now what you will do is either you will move this object to bring it to near this object, and what you will do is you will select a point of reference of moving. So generally this will be your point of reference. So this point will move to this point. That is what we call as transformation. That is moving the object. Either this will move or either one or first object will move or second object will move. So transformation has happened. Once the transformation has happened, we will use the join operation and get the desired product. Is it clear? Now this is the sequence of operation that you actually perform. Now how a CSG tree is going to be developed? Now let me draw a CSG tree for that. So I will start with block 1. That is first thing. I will perform scaling. Okay. Similarly, there is block 2 that has also been scaled. Okay. I will perform union operation and get desired product. So this is how the whole CSG tree actually looks like. For a chain of command or sequence of operation, this CSG tree can very easily replicate how this object has been made. So we are using basically two things. If I want to add the two objects together, then I am either doing A union B or A plus B. If I'm taking the intersection part, then it is A intersection B. And if I am subtracting one object from another, that is A minus B. Every CSG, every model constructed through solid geometry, that is CSG method, has a CSG tree associated with it. Every product can be associated with a CSG tree, like this. So this is what actually looks like. There was a block 1, there is a block 2, that was transformed, and then it was added or union, and you get the desired product. So if I don't know this product, if I look into this tree only, this tree is more than sufficient to tell me how the processes happen. I created a block. The only thing which is missing over here is dimensions, but generally sometimes dimensions are also added over here. That what is the length, what is the width, and what is the height. That is also added over here for information. Similarly, now this object has been changed to this object where there are two through holes. There are two through holes on both the surfaces. So this is block 1 and this is block 2. So what you observe is block 1 has been created, then the cylinder has been created, they have been transformed and brought together, then they have been subtracted. Similarly, block 2 transformation, cylinder subtraction, and then both these subtracted objects are joined together. So basically, looking at this tree, I can tell you what is the sequence of operation, how this CAD model has been generated. So this is the algorithm which runs behind your modeling process that you actually do in your software. So there are a lot of every CAD model that you can create will have an associated CSG tree with it. It will have an associated CSG tree with it. The simplicity why CSG is so popular is that if you look into the number of options that you have got, these six basic shapes cover almost all the type of surfaces that are needed. Other than that, if you need any specific type of a shape or a profile, then you can simply use the knowledge of your curves to create that specific shape. You can create a B-spline curve and you can make that curve, extrude that curve, or evolve that curve into a specific surface. So you can create a user-defined surface also. So CSG has no foundation regarding which curve to use and which curve not to use. That is the advantage of CSG. So this is a development of a CSG tree, basically. So this is all about solid modeling. Thank you.